Second problem. We're going to look at 3 problems in total today. The second problem is a classic for engineering problems. Inconsistent variability. When experimental errors might be multiplicative rather than additive. Anytime you have a percentage error. So someone says that my value is v equals blah, 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 plus or minus 10%. Then what that's telling you is, well, the bigger the number is, the bigger the error is. Because if this is 1,000,000, I'll get an error that's 10% of 1,000,000. If it's 100, I'll get 10% of 100. 10% of 100 is a lot smaller. And so anytime you get that structure, you're going to have variability that's not consistent depending on the value itself. But fortunately, there's a nice way to handle that. We're going to take a look at some pressure versus temperature data next. So I'll show you the data here first in Excel. The idea is we're going to measure the pressure in some chamber as the temperature is boosted up. We're going to do it a bunch of times. And so we have some reproducibility. We can close this window here. And we've got a script already that'll do this for us. It'll load and plot the data. There we go. So this has temperature down here, has pressure of some locked chamber on top of it. And it's not totally obvious here, but if you look closely, you can see that the spread seems to increase as we move left to right. Now that is more visible if we do our fitting and show the residuals. So we'll do our classic basic fitting, we'll do a linear fit, and we'll add the residuals with scatter plots. There we go. Now, the color choice is a bit annoying, but there it is. If we go down to this end, the data clusters are a little tighter. As we go further and further apart, there's a data point way up there at the top, and then the 4 data points down here are spread out quite widely. This is another classic case where the data will not be weighted equally when we try to fit this. And I can show you why. If I look at this cluster of data points here, in fact, they're very close together. So in some ways, you'd say, this data is the best data I have. It's the most consistent. I would like my line to go through those for sure. But if you look at the residuals, most of them are actually below the line. Most of those points are actually, sorry, the line is below those points. Why would the fit do that? Well, because it doesn't have the same priorities we do. When we go out to this far end, and we look at the data up here, it's doing its darndest to try to get this furthest data point close to the line, and this furthest data point here close to the line, because further spread, when you square it, becomes even more important to the fit. And so all the stuff up here, because it's going to have to be further away from the line because it's more variable, is going to have more of an impact. And that's bad. Because then when we go and look at the fit and try to interpret the numbers, when we do that number, and we see this number, this 2 minus 50, well, is it really 2, or should it be something else because these guys are getting overweighted? I really like the data down there better, so why shouldn't I prioritize it? And that's our problem. We need to prioritize the data equally, and having different spreads as we move from left to right is causing us not to weight the data equally. So first off, the relationship between temperature and pressure should be PV equals nRT. So it should be linear. If I tell you the temperature, I should be able to figure out the pressure of a nice ideal gas in a closed environment. One answer to this is to take logs. All right? So what we're going to do, explain why that makes sense in a second or two, but for now we're going to simply do that transformation. We're going to take our data, and before we do the fitting, we're going to take the log of both sides. We're going to take the log of the temperature and the log of the pressures, and we'll see what that gives us. Now MATLAB, of course, has functions built in. They're not the ones you'd expect. Reminder, remember ln in math world is log in MATLAB, log base 10. In our normal world would be log 10 in MATLAB explicitly. And that's very common amongst programming languages. So what we're going to do is take the log of the pressure, take the log of the temperature, and plot that instead. When we do that, and we do our tools basic fitting, and we fit our linear plot, and we plot the residuals, now, life is so much better here. As you move from the low end to the high end, the data has roughly the same spread. And that means that the data down here is going to be treated just as importantly as the data here, because they're all about evenly spread around some center. And you can see that the line actually goes more traditionally through the clusters of each point. Now this guy's a little bit below, but it's also out of sync with the rest of them in terms of a straight line. It looks better. The fit is better because our residuals are well behaved. They fit the model that we're expecting the best fit to be the best fit for. So the log transform really did a huge improvement here because it took care of the scaling, the fact that as we move from left to right, the data spread out. The log took care of that and made the spread roughly even as we went from left to right. Never be perfect because the data has noise in it, but it looks much more commensurate now. What I will point out is there's a really good mathematical reason why this makes sense. If you said my pressure is some constant times my temperature, but then I multiplied by some number like 0.9 to 1.1 or something, so that'd be about a 10% error. That's what we're imagining. This is the error here. Effect. We're saying if there weren't little gremlins in our machines, the pressure I could calculate exactly as some constant times temperature, nRT over V, whatever. But because there's measurement error, there's experimental error, all sorts of things, somehow I'm going to take that value and I'm going to multiply it by plus 10% or minus 10%. And that's going to be the effect. So why does log help this? What happens to that multiplication when we take the log? What does it turn into altogether? Addition plus, exactly. When we get log of p now, let's do it this way, sure. Log of p should equal some log of kt, that's fine, plus log of some error effect. And these numbers are all in the same range. So we're going to add or subtract. Numbers less than 1 turn out to be negative. We're going to add or subtract roughly the same number every time. So it'll be numbers between 0.9 and 1.1. So these values here are going to be the range of the data that we see. If I have a 10% error on my log plot, I'm going to get consistent plus or minuses instead of consistent multipliers. And that relationship of multiplication turns into addition with logs is exactly what we're taking advantage of when we do these transforms. So anytime you have a percent error, you almost always, I cannot think of a case where you would not take the log of the data so that percentage error becomes a plus or minus the same error in the log scale. There are times when you do more exotic things like 1 over x or lns and stuff like that. But the key thing in all these things is to understand the source of the error. Here, it makes sense that my temperature sensor only works to a percentage error. It's not absolute within plus or minus x degrees. Well, then if I know it's a percentage error, I should take logs. I absolutely should, and in fact, I probably have to make this analysis make any sense, because I know that will turn the bad multiplicative error into the perfectly appropriate error for a fit now, which is constant variability, constant range of error.